Okay, so it should be recording now, yes. So welcome to Math 383 Complex Analysis. This is lecture 32. So what I want to do today, we've got a lot to do, is I want to cover the end of the applications to probability, talk a little bit about applications to differential equations. So for the exam, there are a lot of topics we're doing for the final third of the class. You are not responsible for any of them exclusively on the final. There will always be a choice of do one of the following. And the final is open book, open notes, so you can always look things up. Okay, yes?
I saw your email. The first 4 problems, is there no time limit for that?
There's no time limit for those. Okay, so I'll talk about the exams later because I want a lot of stuff I've got to get through today. Okay, so what I want to do is I want to finish up the probability stuff. So the first we need to do is we need to evaluate the Fourier transform of the standard normal. Okay, is there any value of t where this might be easy to do or something you've already seen? 0. Have people seen the trick to do this when t equals 0? If you let I be 1 over the square root of 2 pi integral minus infinity to infinity e to the negative x squared over 2 dx, then I squared is 1 over 2 pi integral minus infinity to infinity, and I'll write x equals e to the negative x squared over 2 dx, integral negative infinity to infinity, and I'll write y because I have to do a separate variable, y squared over 2 dy. This is 1 over 2 pi. And now, instead of integrating over the xy plane, I have e to the negative x squared plus y squared. Oh, that's just e to the negative r squared over 2 r dr d theta. R goes from 0 to infinity. Theta goes from 0 to 2 pi. And life is good. Because when you do the polar change of variables, you have an r dr. You have an e to the negative r squared. So everything works out perfectly. And when the dust settles, you find this equals 1. So again, go through, do all the details of this. So if I squared equals 1, what does that tell us about I? Plus or minus 1. But then that corrects to it's just actually 1 because we know I is greater than or equal to 0. So it has to be the plus 1. So this has evaluated the Fourier transform at t equals 0. We need to do it, however, for other choices. Okay. Anybody have any thoughts about how to do this for other values of t? Anybody know a good value of t to put it in? Nope. Because you would then have to still do the calculation. Nope. You all are implicitly assuming something about t. What are you assuming about t? What are you assuming? What are you assuming about t? It's real. What should you take for t? What should we take for t? Try t equals ix. Or maybe it, maybe. Or if you want to use another variable, maybe iy. Okay. And so if we do something like that, now we would have the 1 over square root of 2 pi integral from minus infinity to infinity e to the negative x squared over 2 e to the minus yx dx from t equals iy. Can we do this integral? Yeah, of course, right? We've got integration skills. So let's put it all in the exponential. So I'll have negative 1/2. I have x squared minus 2yx dx. And I've probably left a giant space for a reason. What should I put in the giant space?
Plus y squared minus y squared.
Yeah, plus y squared minus y squared. I've added 0. And so if I do that, I now have 1 over square root of 2 pi integral minus infinity to infinity e to the negative x plus y squared over 2, e to the, now I've got a negative y, a negative 1/2, so that's going to be e to the y squared over 2 dx. So I have an e to the y squared over 2, 1 over square root of 2 pi, integral minus infinity to infinity. Well, when I'm looking at the integral of e to the negative x plus y squared, this is the same as e to the negative x tilde squared over 2 dx tilde, where x tilde is just x plus y. Just change variables. Oh, yeah, it should be x minus, yeah. It should be x minus y. It's not going to change anything, but you are correct. It should be x minus y. What's this integral going to be?
1.
1. I've got the square root of 2 pi outside. And so that's just equal to 1. So this whole thing is just e to the y squared over 2, or since t equals iy, that means y squared equals negative t squared. Yes? This is just e to the negative t squared over 2. Right? So we know, looking at our integral, if t happens to be equal to y, to I times y, we know what the answer is. What theorem can we use? Accumulation. So I'll let you put in the rest of the details, but because we can evaluate this at I times y, we know that it has to agree everywhere else. And the integral is clearly going to converge because no matter what I put in for t, even if I put in t as a complex number, the e to the negative x squared over 2 is going to have a lot more decay than the e to the itx can be for any fixed t. So by accumulation theorem, I know that this is true when t is pure imaginary, so it must be true for all values of t, including t real.
Wait,
yes.
Are we assuming y to be real?
Here, yes, y is real.
Why can't we assume y is? What if y is in like complex?
Well, if y is complex, then we can't do the integration on the next page. On this page over here, because everything is real, this is an integral we know how to do. So because we know how to do the integral in this one case, we can integrate e to the negative x squared over 2. We can integrate e to the negative x minus y squared over 2. We can do those integrals. We don't know how to do an integral with a mixed, real and imaginary part. So by choosing t to be I times y, I now have an integral that's entirely real that I know how to do. And by the accumulation theorem, because it's true for all values of t that equals I times y, where t is pure imaginary, it's now true because it's holomorphic for all values of t. And so we've now calculated the Fourier transform. So if I gave you an exam question like this, this is a probability question to some extent. I'm not expecting you to have taken a probability class. It would be nice if you would do that. It's a wonderful subject. This is a legitimate exam question to give you, even though it depends on probability. You don't need to know probability to actually do it. It has wonderful applications to probability because it's the Fourier transform of the Gaussian. Yes?
I can see why this converges everywhere.
You need to show it's holomorphic. You would have to show it's holomorphic as well. But again, you have so much decay that you can justify differentiating under the integral sign. And then when you differentiate under the integral sign, everything is still going to converge. So this is complex analysis at its finest, right? We got the Fourier transform of the Gaussian essentially everywhere just by knowing it at t equals 0, by then noticing that we had a nice translation and then using the accumulation theorem. So again, I'm trying to show you what you can do with what we've learned. When I was an undergraduate, I had a full year of complex analysis. We're trying to squeeze everything into one semester, right? No way to do all of that. I'm trying to just flag for you what's out there. We can calculate Fourier transforms. So now, one of the questions is, why do we care about Fourier transforms? Well, let's say we have h of x is f star g of x, which is the integral from minus infinity to infinity of f of t g of x minus t dt. Okay. I'm going to assume that all of my functions are so good that anything I want to do is justifiable. And then later you can figure out what is the weakest set of conditions you need to justify everything that I want to do. But just right now, everything I need to hold holds. If you want, think of the functions as Schwartz, rapidly differentiable, infinitely differentiable, rapidly decaying, everything is fine. Let's calculate the Fourier transform of h. So that's going to be the integral from minus infinity to infinity of h of x e to the negative 2 pi I xy dx. Oh, that's the integral from minus infinity to infinity. Now, this is the integral of x. Now I substitute, what is h? That's going to be the integral t goes from minus infinity to infinity, f of t, g of x minus t. I'll put the e to the negative 2 pi I x y dt dx. And by now you've probably realized I actually haven't learned that much in my life. I'm close to a one-hit wonder. I really can't do that many things. What should I do now? Minus t plus t. Right? I've got an x minus t. So if I write it like this, now if I start seeing this, so let's see, I'm going to have the integral x goes from minus infinity to infinity. Now, do I want to integrate first with respect to t or first with respect to x? I'm going to integrate with respect to t first. And the reason you should know to do that is because this is a multivariable calculus problem. One of the only things we know how to do in multivariable calculus is switch the order of integration. So if I integrate with respect to t first, no, with respect to x first, okay. I'm going to have f of t, I'm going to have an e to the negative 2 pi I ty. I'm going to have the integral x goes from minus infinity to infinity, g of x minus t, e to the negative 2 pi I x minus ty dx dt. So what is the bracketed integral equal? I'm sorry? Yes, you change it, and what do you get?
Convolution with delta function?
Nope. Okay, the Fourier transform, you got to be more specific. The Fourier transform of evaluated at?
E of x minus t.
Nope. I'm integrating out x. Why? So just let u equal x minus t, then you get the integral u goes from minus infinity to infinity, g of u, e to the negative 2 pi I uy du. So this piece over here is just g hat of y. What's this piece over here? This one's easier. F hat of y. So the Fourier transform of the convolution is the product of the Fourier transforms. I love integrating just as much as the next person, if the next person happens to be a pure mathematician, right? Most people are not thrilled about integrating for good reason. If I wanted to be cruel, and frequently I do, can I give you a very difficult integral? Yes. I actually have to work hard to give you an integral that can be done in nice closed form. You know, Calc 2 is the class of the big lie, where you think you can integrate when you're done taking Calc 2. You can't integrate. I can't integrate. Most functions don't have a closed form antiderivative. Can you differentiate? Yes. I can't stump you with a derivative. You can just keep hacking away with the rules of differentiation. No matter what I give you, it's going to work out. So integration hard, differentiation easy. What does the Fourier transform do? The convolution, this is a key concept in probability. This was a key concept in our Fourier convergence theorems. It involves integration, which is hard. the Fourier transform converts convolution to multiplication. This is known as progress. Okay, I would much rather multiply two things. And then what you can do is you can pray that you can actually calculate the inverse Fourier transform. And then if you have something like this, then you can come backwards. But the Fourier transform converts multiplication, converts convolution to multiplication. All right, so we can use this to give a sketch of the proof of the central limit theorem. I am not going to go into great detail on this now. At 1 o'clock, I will talk more about this. If anybody is interested, I will post the video for that. And so imagine we have variables, xk, ii, rv. That means independent, identically distributed random variables. Without loss of general, I'll say they have mean 0, standard deviation 1, finite higher moments. I'm going to say everything is going to be good. I will let Zn be x1 plus xn divided by n. And the central limit theorem says that this converges to being a normal with mean 0 and variance 1. If I've done everything correctly. I believe this is the correct normalization. I might be off by a square root of n somewhere. I think this is right. Or maybe it's square root of n down below. I think it's actually square root of n down below.
I don't think so.
No, okay. Yes, okay. So this should be, this is the average value. Yes? Well, no, because I'm saying that the variance here is going. Okay, so each of the x's has variance 1. So if I have a 1 over n, it's going to sum to n over n squared. So I think I want a square root of n down below so that this quantity has variance 1. Because the variance of a sum of independent random variables is the sum of the variances. And so because each has a 1 over root n, the 1 over root n gets squared to be a 1 over n. So this is the quantity that will converge to being normally distributed with mean 0, variance 1. Okay.
Yeah.
Yeah. If I'm off by a square root, it does not matter right now. Okay. This is meant to just be a high level. How do we go through things here? But basically, the variance of a sum of independent random variables is the sum of the variances. Since each xi has variance 1 and then multiplied by 1 over root n, you square the quantity when you're calculating the variance. So you would get a 1 over n from a 1 over square root of n. You have it n times, so the variance would end up being 1. So you can double check that. If I see at least one person nodding that I've got things normalized correctly. So I'm pretty sure that this is the right normalization. If I'm wrong, I'm wrong. It just changes the algebra a little bit. So what we can do is we can look at the moment generating function of x1 plus xn over square root of n of t. And then, this is the nice thing about lecturing like this. I should have somewhere, a slide where I have some stuff. Oops, it was a little bit later about. Here we go. The moment generating function of a sum is the sum of the moment generating functions, and then the moment generating function of alpha x is the moment generating function of x at alpha of t. So when I use those two facts, this is going to be the product, k goes from 1 to n, the moment generating function of xk over square root of n of t, because the moment generating function of a sum. And then that's going to become the product, k goes from 1 to n, of the moment generating function of xk at root n times t. And now what's nice about this is if you think about the moment generating function, as t just becomes a little bit away from 0, it's going to be magnified tremendously. Let me just make sure. I'm sorry. Is it t divided by square root of n? Sorry. So if I have alpha x, it's alpha t. So wait. So yeah. Sorry. So it should be. it should be t over square root of n.
Somehow I think it's square root of n times all those sums.
No, when I'm plugging in, it should be t over square root of n.
No, as in the random variable you're defining like z, it should be square root of n times the sum.
No.
Close.
I'm pretty sure this is going to work. And so now, we would want to calculate what's going on here. Okay. When you have something like this, how would you handle an expression like this? Log. And so you can take the log, and you can try to understand what is the moment generating function going to. These are all going to be the same. So if they're all the same, this would just be the moment generating function of x at t over square root of n raised to the nth power. And so we just want to understand, what does this look like? And the idea is to show that this is converging to the moment generating function of the Gaussian. And now what you would love to do is to say, if two functions have the same moment generating function, what must be true? They must be the same. And that is the case if things are nice. You need some results from complex analysis to invert backwards. So again, right now I am trying to just give you high level of how all of this comes into play. Is I want to understand something like this. I could write things down directly and say, if I want to calculate the density of a sum, ooh, what do I use to calculate a density of a sum? I use a convolution. And the Fourier transform of convolution becomes multiplication. So I could attack this by taking the Fourier transform of z in the very beginning, and that would convert the density to a high product. And then I show that that's converging to a Gaussian, and then I invert. And what did we just do earlier today? We just calculated the Fourier transform of a Gaussian is a Gaussian. Okay? And then you basically want to just pray that there's nothing else. So if I have two functions, and they both have the same Fourier transform, then their difference would have a Fourier transform of what? So if f and g both have the same Fourier transform, f minus g would have a Fourier transform of 0. So the hope is the only thing that has a Fourier transform of 0 is 0. So if you restrict yourself to a nice space, that should be true. This is why we have some results in Fourier analysis where we say, like Bessel's inequality, the sum of the f hat absolute value squared is the L2 norm, the integral of absolute value of f squared. Well, as long as my function is not equal to 0, then I can't have all the Fourier coefficients becoming 0, because I won't have that equality. So you just need some way to get to some kind of uniqueness and to avoid some difficulties. Okay, there's a lot more that can be said about this. I will go through this very slowly at 1 o'clock for anybody who's interested. Nothing at this level would be on the exam. I just want you to get a sense of how complex analysis can apply to prove the central limit theorem. And I've posted the detailed calculations of how to do it. There's several ways. One is to work directly with the moment generating function, take a logarithm, expand it out, show that it's converging to a Gaussian. And you can do the algebra that way. The other way is to take the Fourier transform of Zn and say the Fourier transform of the convolution is the product of the Fourier transforms, show that that is converging to the Fourier transform of the Gaussian, and then go backwards. Yes?
Aren't these two pretty similar?
They're very similar.
Characteristic function is basically
the characteristic function is basically the Fourier transform. Exactly. So they're all extremely related. It's how do you want to do your algebra? For a lot of functions, we actually explicitly know what the moment generating function is, which makes this really easy. But sometimes we don't, and we have to just do things in terms of general algebra. So what I want you to get from this is that these can be done. And there's a couple of different ways of arranging the algebra depending on what we want to do. All right. I now want to turn to some more applications of everything that we're doing, solving differential equations. So how many of you have taken physics and seen equations like this? Can anybody tell me which equation this is? Yeah, I was going to say, it's, if you're able to read fast, it says the heat equation over here. So this is the heat equation. So we want to try to solve differential equations like this. And the idea is that the Fourier transform has a lot of wonderful properties. And so if g of x is f prime of x, and h of x is x times f of x, so one of them is the derivative, one of them is multiplication, then there's really nice relations between the Fourier transforms of g and f and the Fourier transforms of h and f. So it says g hat of y is 2 pi I y times f hat of y, and then the derivative of f hat of y is just negative 2 pi I h hat of y. Okay, so we can go nicely between these different functions. And so, for example, let's say we have, I'll just prove one of them. And I'll leave the other for you. So let's say g of x is f prime of x. Then the Fourier transform of g at y would be the integral from minus infinity to infinity of f prime of x e to the negative 2 pi I xy dx. And what are we going to assume about f? What will we assume about these functions? Yeah. Nice. If you don't like nice, you could say good, right? Whatever conditions I need. So decay at infinity at a decent rate. So that the integrals converge. And I'm going to assume that they're going to 0 as I go further and further down. How should we handle this integral? So I don't want an integral in terms of f prime. I want integrals in terms of f. Integrate by parts, right? You're allowed to hate partial fractions. You're not allowed to hate integration by parts, okay? This has to be one of the methods of integration that you like, okay? What's your favorite method of integrating? Contour integration. This is a class in complex analysis. You should be convinced by now, right? A lot of times the way you do standard integrals is you convert them to contours and then you reduce it to algebra. Well, there's always 2 years from now. All right. Do I want u to be f prime of x or do I want dv to be f prime of x? Yeah, I don't want u to be f prime of x. So dv will be f prime of x dx. So then v will just be f of x. So u is e to the negative 2 pi I xy. So du will be negative 2 pi I y e to the negative 2 pi I xy. So then we get g hat of y. It's uv at minus infinity infinity minus the integral of v du. Well, what's true when we evaluate at minus infinity infinity? More than just something nice. Yeah, it's 0 because of the decay. So we're assuming decay. And now for what's left over, oh good, the minus sign is going to be reinforced with the minus sign there. We have a 2 pi I y. Well, that has no x dependence. We can pull that outside the integral. And we're left with the integral from minus infinity to infinity of f of x e to the negative 2 pi I xy dx, which is just 2 pi I y f hat of y. And so here's the proof that the Fourier transform of the derivative is just multiplication of the Fourier transform. This should give you a hint as to why the Fourier transform is so useful for solving differential equations. Rather than having to deal with derivatives, I now just have to do multiplication. That's not bad. That's a good trade-off. Okay. And then the other one is that if I have multiplication, that's the same as a derivative. So I can go back and forth. So if I give you something involving derivatives, I can replace that with just my Fourier transforms. Okay. So what I want to do now is I want to define the Laplace transform. How many people here are taking high-level physics classes? Okay. So depending on where you are, I know we have at least one student, but they're not here today. So depending on who you talk to, things can be defined slightly differently, so you always have to be careful. So the Laplace transform, I give you some function f. The Laplace transform of f at s is the integral of f of t e to the negative s of t. It's really the case of a integral kernel. And here, my integral kernel k of st is e to the negative st. So what I really have is I have the integral from 0 to infinity of f of t, k of st dt. We've seen stuff like this before when we did the approximations to the identity, when we did Fayet, when we did Dirichlet. There we had kernels that depended only on the difference of the two variables. Now I have a kernel that depends just on their product. Does this look like anything you've seen before? What does this look like?
It's the complex it's the probability generative characteristic function thing.
Almost. So if we do it like that, that's supposed to be from minus infinity to infinity, but we could only be, maybe we're just looking at functions that are just defined from 0 to infinity, so that's absolutely fine. So this looks like the moment generating function. What else have we seen that's really similar to the moment generating function? It was just mentioned a few moments ago by someone. Characteristic function. And because we're not probabilists, what do we call the characteristic function? The Fourier transform. So the only problem is, this is from Wikipedia, source of all wisdom, fountain of all knowledge. Unfortunately, keeper of the physicists' convention. And so they are defining the Fourier transform without the 2 pi and the exponential. So you have to be careful. I am not advocating that we have a massive attack of Wikipedia to try to change the definition of the Fourier transform. If that happens spontaneously, so be it. Be careful when you look at things as to how things are normalized. The Fourier transform in Wikipedia is normalized without the 2 pi factor. Not a big deal. It's basically the Laplace transform is essentially the Fourier transform. The difference here is in the Laplace transform, we have S, here we have basically I omega. Now, when we do the Laplace transform, if S is real, if S is greater than 0, then we're going to have some exponential decay. If S is less than 0, however, we could have exponential growth. So it's not necessarily clear that this will always converge. If F is a probability distribution and S is positive, then it's going to converge. But we could have some issues as we try to extend this. So is there really much of a difference between the Fourier transform and the Laplace transform?
Just make the variable complex instead of that.
Right, but if we more generally just consider complex values of the Fourier transform, then they're the same. It's just a slight different notation as to what we're calling things. So depending on which problem you have, sometimes it's more convenient to have things in one form than another. There's also the Mellon transform, which is, again, very similar to all of these. Sometimes it's through a logarithmic change of variables. And so if one thing has a property, frequently another one has the property as well. And so they will have nice properties in terms of the convolution of, and then the Laplace transform will be very nice in terms of products of Laplace transforms. But it's essentially the Fourier transform. So because the Fourier transform is nice with respect to derivatives, is nice with respect to multiplication, the Laplace transform should be nice as well. Okay, so there's a bunch of tables of properties of functions in the Laplace transforms. And so frequently, the convention is use the lowercase for the function and uppercase for the transform. So you just have to be careful when you're looking at it. This is not the integral. Well, it is an integral, but it's the Laplace transform integral. So little f goes to big F. And then I think I can zoom in a little bit. So if I have t times f of t, the Laplace transform of that is negative f prime of s. And then if I want to look at the Laplace transform of f prime, it's going to be s f of s. Just view that as f of 0. Don't worry about the technical stuff Wikipedia is worrying about. Just evaluate that at 0. So the Laplace transform of the derivative is basically just s times the Laplace transform minus a constant. And then do shampoo mathematics. If I want to take the Laplace transform of f double prime, well, first I take the Laplace transform of f prime, and then I still have an f prime, so I have to do the Laplace transform again, and so I get a polynomial of degree 2. more generally, I can take the Laplace transform of the nth derivative, and I'll get s to the n times the Laplace transform minus a polynomial in s times constants. Little f, k minus 1 derivative at 0, that's a constant. So what the Laplace transform allows us to do is to convert a derivative to basically multiplication, and polynomials. And so now, instead of trying to find f, little f, I'm trying to find big F. So the hope is that I can find big F as a function of s. And so if I want to find what function f satisfies this differential equation, I no longer try to find the function little f that satisfies the differential equation. I find the function big F that satisfies the Laplace transform of the differential equation. And what do you do now that you have the Laplace transform of the solution? And how do you transform it back? Use the table, or more formally use whatever the hell it is, you use the inverse Laplace transform. And so if you're lucky, when you solve for the Laplace transform, you get something that is in a table of Laplace transforms. And you know that it has something unique that it came from. And so I am old enough that when I was in college, one of my physics professors told me, and I might have shared this, that you have to have two table of integrals, a small one that you keep on you at all times, and a big monster for your dorm room. Everything is online now. Things are very different. But a lot of work has been done to tabulate these transform pairs. And so if you can invert, and what technique, what subject do you think is going to be useful for doing these inversions? Complex analysis, right? There's a reason why I'm teaching this in complex analysis. Is you use techniques from complex analysis because we're doing these integrals. And so you complete the contours, you shift things, you get things from residues. So again, this is not a class in differential equations. But given the prerequisites for differential equations do not include complex analysis, almost surely this is something that's typically not covered. I think it was covered when I took differential equations as an undergrad before complex. I know I covered it when I taught differential equations here, just because it's worth seeing that you can do stuff like this. Okay. Yes?
What is the Laplace transform for integral transform? Like convolution? Because we know that like the Fourier transform.
Right, so we will get to that very, very shortly. Such as right now. And so if I look at the convolution of f and g, the Laplace transform is not surprisingly the multiplication of the Laplace transforms. And the reason is the Laplace transform is the Fourier transform with an output, right? So it has to have the same property. It has to be structurally the same because I'm just changing how I write my variables. So this tells you that the Laplace transform is going to be useful for a lot of things as well. Okay, so just for completeness, I'm just trying to have a bunch of these things written down. This is just some blabbling from Wikipedia that the Laplace transform and the Fourier transform, they're really the same thing. And then tables of Laplace transforms. So I give you certain functions, and so here you've got to figure out what is u of t. U of t is like a unit step. I don't want to get into what all the stuff is. There's just a whole bunch of things. I think the next page is more standard stuff. Yes, where they give you functions and you can figure out what the Laplace transform is and back and forth. So these are just tables. These force you to just do certain integrals. If the function isn't too bad, you should have no trouble integrating it against an exponential. Especially if your function's a polynomial, or your function's another exponential, or maybe your function's a Gaussian. There's lots of things where you can do the integral in nice closed form. This is one of the reasons when we do a lot of mathematical modeling, we use certain probabilities. It's because those are the probabilities that lead to integrals that can be done in closed form. Okay. So the homework asks you, I think, to do 3 out of the following 5 problems. So the first problem is find the Laplace transforms of the following. How can you do this? How can you do problem 1? 2 acceptable types of answers. So one is basically integrating by parts. lookup table, Mathematica, something like that, right? This is the 21st century. You should be able to do these integrals directly, but you should be able to check by using something like Mathematica or using a lookup table. For the second, find the inverse Laplace transform. So one thing is to look up a little bit and see how do you find the inverse Laplace transform. And so I'll share a video from one of the times I've taught this class where I go through and talk about how you do the inverse Laplace transform. It's basically just doing another contract. But all of these can be done very nicely from the lookup tables. I just want you to get out of this the power of what you're learning. We are learning a tremendous amount in this class, and we're not learning it for stuff in a vacuum. This can be used to solve differential equations which describe how the world operates. The next three are a little bit harder. They want us to use the Laplace transform to solve certain differential equations. Okay, and so I'll share a video where I go through slowly and solve some of these. What you might notice is these all look very similar. They all involve, two derivatives. They don't have any nasty things in front of the y prime or the y double prime. I don't have, some function, cosine t times y double prime of t. That would become a little bit harder to deal with, but we could hopefully do something. Okay, these are simpler differential equations to solve because this is not a class in differential equations. I just want you to be aware that you can solve equations like this. So how many of you have taken differential equations? Right. Did you have to solve stuff like this y double prime plus y equals f of t? Okay, that's something you should have learned how to solve, and there's various techniques you can use. What you can do is you can do the Laplace transform, which will convert this to a polynomial problem. And then you invert at the end. Okay, so there's a video that's going to go through this very slowly. What I want to just do at the very high level, let's see, where do I want to do it? Just at a very high level. So let's say I wanted to solve, okay, there we go. I keep showing page 61 of 153. In the upper left, it says y double prime minus y minus y prime minus 2y equals 0. With initial conditions y of 0 equals 1, y prime of 0 equals 0. I have a second order differential equation. If I give you two pieces of information, that's enough to determine uniquely what's going on. Normally, those two pieces of information are your initial location and your initial speed. But I could give you your position at two different times. And what I do is I take the Laplace transform of both sides. So I'm writing over here because I was teaching this in differential equations. We have reason to believe that it's related to the exponential function. And the reason is if you take the derivative of e to the RT, you're just going to get some constant times e to the RT itself. So y double prime, y, they'll all have e to the RT to the same thing. When everything comes down, it's going to work out nicely. You can do Laplace transforms to solve a lot harder problems than this. The goal is to just take something where we have some intuition and we can check our answer at the end of the day. So we apply the Laplace transform, and the Laplace transform is a linear operator. The Laplace transform of a sum is the sum of the Laplace transforms. So I have the three different pieces. And then we use the result I mentioned that the Laplace transform of a derivative is going to be s or s squared, depending on how many derivatives we have, of the Laplace transform, and then a polynomial involving the function and its derivatives. So again, at a high level, I just use what is the Laplace transform of y double prime, what's the Laplace transform of y prime, what's the Laplace transform of 2y, which is twice the Laplace transform of y. And so I'm going to call capital Y the Laplace transform of little y. So I get s squared minus s minus 2, putting in the initial conditions for capital Y of s, plus 1 minus s y of 0, minus y prime of 0 equals 0. Oh, so now I put in the condition y of 0 is 1, y prime of 0 is 0. And when I do that, I get y of s, capital Y of s, the Laplace transform of my solution is just s minus 1 over s squared minus s minus 2. Well, I can factor the denominator. And you can, at this point, realize that this was a cooked up problem because the denominator factors so nicely, right? And then I use partial fractions. You are allowed to hate partial fractions. You know, this is typically the least favorite integration technique. It's useful for a lot of things, but I can write this now as a over s minus 2 plus b over s plus 1. And then this is where you go through and remember your calculus from long ago. And you figure out that it's going to be, okay, 1/3, 1 over s minus 2 plus 2/3 over s plus 1. And now we use our lookup tables. I know the Laplace transform of e to the at is 1 over s minus a. Ah, okay. So I can then use that to figure out if I take y of t to be 1/3 e to the 2t plus 2/3 e to the minus t, then when I take the Laplace transform, I'm going to get exactly what I have. So this is how we can use the Laplace transform, or essentially the Fourier transform, to solve some differential equations. It would become a lot more interesting if instead of having y double prime minus y prime minus 2y equals 0, I had it equal something depending on t, say f of t. And then I would have more terms and it would be more involved. And then finding the inverse Laplace transform would be a little bit more work. Right, there's nothing wrong with that, just a little bit harder. So at a high level, this is, you know, a great application of what we've been doing. Right. So for the last minute, if you've already emailed me the solution to this, you know, please don't speak up. We have endpoints somewhere on the circle. Find a point x, y on circle such that the product of the distances to the points is at least 1, or prove a point exists. So here's P1, P2, P3, Pn minus 1, Pn. So prove that there is some point on the circle so that no matter where I put all the other points, if I look at the product of all the distances, it's at least 1. So the way I'm phrasing it, I'm telling you there is such a point. Unit circle. Now, you could try to do this by maybe inducting on the number of points. If there's 1 point, it's clear. If there's 2 points, you could try to look at all the different configurations for 2 points, 3 points, and so on. You know, the problem is, as p gets very close to one of the points, what's going to happen to the product? Yeah. What's the largest one of these factors could possibly give you? Nope. 2. Right? So if you get too close to any of points, then it's not going to be enough to be compensated by everything else. So any thoughts about how we can study this?
If all the points are equidistant, actually,
they're not.
N-gon, the product is going to be 1, I think. So maybe we should.
Well, but no, the product won't be 1 if they're all equidistant. It depends where you are.
If we're on one of the vertices.
If you're on one of the vertices, the product is 0. Because then your distance to that vertex is 0. Or if you're just slightly away from that vertex, the distance is going to be small.
This is an analysis class, so we can like make the product of the distance as a function depending on p.
Okay. So I'll write my p as maybe z for some point on the unit circle. So my function of z will be the product, k goes from 1 to n, or let's say z minus zk. And I want to study the absolute value of f.
Do we know the endpoints first, or do we have to pick this p before?
You know where the points are, and then you have to choose where p is.
Oh.
So what kind of function is p of z? Holomorphic. What do you know about a holomorphic function? Choose the maximum value in the boundary. Can anybody give me a point in the interior where it's easy to calculate the product of the lengths? Yeah. So if we look at f of 0, the absolute value of f of 0 equals 1. Oh, right. This is a great way to end right before Thanksgiving. This does not look like a problem for complex analysis. But we know that the value, if I evaluate the function at the origin, the product of all the distances is 1. It achieves the maximum on the boundary. In fact, we can prove something even stronger than there's a point on the boundary where the product of the distances is 1.
It's at least
Greater than 1, because we can make the product smaller than 1 on the boundary. So we're here. Here. Do we know that the product is 1 everywhere? No, because we can get arbitrarily close to one of the points. So because the function is not identically 1, it actually has to be larger than 1 somewhere on the boundary. So we can actually prove it has to be larger than 1. This is an absolutely wonderful, spectacular application of complex. So we did a tremendous amount today. I got to go home and deal with a few things. I will be back at 1 o'clock for an optional session on probability. I am happy to have as many of these sessions as people want. I will record them. The goal is to show you what you can do.